For everybody online, we are going to wait a couple more minutes before we start.
Hello. Hi. How's everybody doing? Cool. All right, we're going to go ahead and start. So, last week we did offensive security, like a super high level. Got about, I want to say 2/3 of the way through. But yeah, we're going to finish that up today, and then we're going to go over cryptography, or start on cryptography with our friend over here, our tech advisor, Trip. But before that, we've got a couple of events coming up that I think you all should know about. So, Ethan, never mind. Take it away, Ethan.
All right, so our first event is Down Under CTF, and that is happening this weekend. So it is CTF that's put on by a few different security groups in Australia. They're targeting like their secondary and tertiary schools over there. So it has a wide range of difficulty, starting with some basic encoding that you might see that Tripp might talk about today. I don't know if he's going to talk about. I don't think he'll talk about encoding, but some basic cryptography stuff. It's also got some more complex things that like ROP, if you know what that is, return-oriented programming. They actually have some libc attacks, or at least they did last year. So it's a pretty good range of, if you're a beginner, there are going to be challenges that you can do, and if you're a little more advanced, there should be some things that should challenge you and really make you think. So open to anybody and open to all skill levels. Again, it is this Friday. It's when it starts. It starts at 4 a.m. They are in Australia, so they're on a slightly different time schedule than we are. And then it ends Sunday at 4 a.m. as well. So,
does everyone know what a CTF is? Does anyone not know? So what's a CTF?
Okay, just to summarize, a CTF, they're going to give you little puzzles, little challenges, and your goal is to solve these challenges and get a flag. So, for example, the base 64, they're going to give you a string that looks like a bunch of garbage, and if you happen to know that this is base 64, or you could go to CyberChef, which I think we may have talked about before, and run magic, which again is not anything technical at all. It is just, hey, let's throw a bunch of stuff at it and see what sticks. Basically, we could get, oh, that's what it decodes to, and that's your answer. Some of them, like pwn-based challenges, are going to be, hey, here's something, break it, or break it in a specific way. Those again are sometimes can be a little more advanced. Should vary pretty good on the type of challenges though.
Are we doing it in person?
So this will predominantly, at least as of now, I plan for it all to be in Discord. If you guys want to get together and work on it in person, feel free to. This is very much all of us work on it together. I mean, AUEHC, we are like a team. We're technically a team. So, work on it with each other. Everybody does. This is not individual. Again, work with other people. We can use Discord chats. If you want to hop in the voice chat, that's great. If you want to just type in chat, like, hey, I'm working on this particular challenge. Here's what I've got. Does anybody have any hints or advice or whatever on ideas that I might could do next? So I know I will try and be in voice chat at least some on Friday working on it. I don't know about Saturday, but again, anytime if you guys are in there, feel free to ping other people and say, hey, I'm in chat working on stuff. Maybe other people hop in there. So, cool. Any questions about that, or everybody good? Oh, one other thing. So the team limit is 5 people. So I have created a team, but we also have a user that will be kind of like a club-wide user, and I will release that info into the Discord. So everybody we can all either use the same user, or if you want to make your own user, make your own team, whatever. I mean, you're also welcome to do that. Again, it's just however you feel like you're learning the stuff best. Because if, say Tripp gets on and solves, I don't know, some of the easier cryptography challenges, well, but maybe those aren't available, and maybe those are something you want to solve. Absolutely, if you're learning, again, the goal is learning, not necessarily can we solve every challenge. If you're learning stuff, if you resolve challenges, that's fine. It's more about trying to figure stuff out for yourself. So, and we'll also be here to help. I mean, we don't have all the answers. We're competing as well, but we can offer tips in some areas. So,
yeah. So the other thing will be SecDec. you guys are probably tired of hearing about it constantly, but we finally have a set meeting time. So we plan to meet Wednesdays from 5 to 7 p.m. I understand that's kind of not a great time, but that's kind of when most people are available, and more importantly, professors could be available to kind of help train us with some of the stuff. Again, kind of like I said in the announcement, they may not all be full 2 hours long like this, and that's what this week is kind of our first meeting for that, and that's going to be a relatively shortish meeting, just kind of probably going to be going a bit more in depth on the short 5-minute spiel you've heard, just kind of talking about some of the stuff that's a little bit more in depth, like stuff we'll need to start preparing and all that. And yeah, so Wednesdays from 5 to 7 p.m. And they will just be over Discord too. So again, even though it's not a great time, you won't have to come to campus at 5 o'clock on a Wednesday to meet in them. They'll just be over Discord, probably just in the general voice channel or whatever. And first meeting is tomorrow. Like I said, so again, reiterating, even if you're not necessarily sure about the competition, everyone is welcome to come. This is not a exclusive club of, oh, if you come, you're on the team, like you're locked in. Like I said, just come, see if it's something that seems interesting. But yeah, anyone have any? Oh,
will those be recorded?
I don't think so.
We'll think on that.
Yeah.
Okay. Let me think about that. We can kind of discuss it maybe at the end of this, and yeah, we haven't recorded in the past. In fact, we haven't really recorded these in the past, like the meetings, but it could be helpful for covering specific topics and just not having to do it every single year. But yeah, let me think on that.
Yeah.
Good question.
Yeah. Any other questions? All right. And yeah, again, too, one more note I actually did want to add is they may not necessarily always be Wednesdays 5 to 7 p.m. Like I think we may try to get some other people, maybe outside or just other professors here, just whenever they're available. So sometimes there may be a meeting or two that isn't at whatever, like it may just be a different time if that's what works. And again, it's one of those things, I guess we'll see about recording them, but I don't know. If you can or can't be there too, usually we can kind of like help fill in on like if you missed a meeting or two, like, oh, this is kind of what we went over and some of the stuff we talked about. So yeah. Well, cool. Turn it over to Charlie. Let him continue the boot camp.
Cool. So last week we went over a lot. So we're gonna pick up where we left off. Briefly, we did like OSINT, reconnaissance, enumeration, Google dorking. I guess that falls into OSINT. And then I think we actually got to intrusion. But regardless, so we ran an Nmap scan on a host on Hack the Box. For those who were there, we're probably not going to do any hands-on stuff because we need to get through the boot camp. But for those of you who weren't here, Nmap is basically a port scanner. So it'll look at a host and it'll check for open services, open network services, check for versioning, check for operating system, check for all that good stuff that you might be able to use to get a foothold on the network. So that's kind of what intrusion is. So you basically look at the service that's running. Maybe you see that it's vulnerable and has something that allows you to get onto that host, get a reverse shell so you can kind of mess around, or perhaps upload something that could then be executed and get you a reverse shell. But ideally, the goal is to get onto the machine, have some control, and then from there, either set up persistence or do privilege escalation. So persistence is what it sounds like. It's basically ensuring that you can stay on the system after reboots. It might be to avoid detection, and if you are detected, to remain on the system. So putting multiple backdoors onto the system, creating users, putting SSH keys on there so you can SSH onto the box. All those good things. And then privilege escalation kind of goes a little bit with persistence, not really, but that's if you land on a host and you're like a common user, or you're a network user. I guess that's not really the name of it, but you are acting as like a service. You might want to go up to a system user so you can actually do more things on that box. So when I say that box, I mean that host. So you can maybe in Windows specifically, a lot of the times to create services, you have to be a system user. So that's one way of persistence. So there's different levels of persistence. We'll get into that later. Privilege escalation, I talked about this a little bit. But yeah, you abuse binaries. That's one way of doing it. You might exploit pseudo rights. So maybe the user you landed on is able to actually run commands as sudo or sudo user. So that might be one way you leverage that to get higher privileges. You might do token manipulation or impersonation in the case of Windows. There's all kinds of really cool ways of escalating privileges and getting what you want out of a system. Are there any questions so far?
So what's the difference between like exploiting pseudo rights and exploiting pseudo itself? I'm talking about the very public.
One of those is
CD.
so exploiting pseudo is more along the lines of exploiting a binary, whereas exploiting pseudo rights would be if a user, it's kind of like I can't think of the term right now. Exploiting the access or the permissions of a user as opposed to exploiting the binary and a fault of that binary.
So like how the system is configured, or how the access control is configured on the system
Versus exploiting a vulnerability within a binary. Yeah. So the question was, what's the there was a vulnerability probably a year ago, I think, that there's an issue with a binary called sudo or sudo, and basically that binary lets you run as a different user or a root user. And the question was, what would be the difference between exploiting that vulnerability versus exploiting the ability to use sudo to get privilege escalation? It's kind of the difference between binary abuse or misuse and accessing or exploiting kind of an issue with the actual security measures on a system. So that's that. Lateral movement. Anybody have any ideas on what lateral movement is without reading that? If I were to land on a system and my goal was to get to a particular, a different asset of an organization, and I've already set up persistence, I've got a reverse shell so I can get back if I need to. I've got system privileges, but I'm not on the system that I want to be on. I can't access the assets directly from the host I'm sitting on, right? What would I need to do to get to that system? Anybody? Laterally move across the network. So lateral movement is basically moving from one host to another. And there are many different methods to use. You could run a command remotely to get a service running on a separate host, or you could run, I think there's a way to run PowerShell remotely. So you could issue a command on a different host and then have it, feed back to like some, I don't know. Lateral movement is basically moving across the network. So you can do the same thing. You can set up persistence on that different host. You can escalate privileges there. And so you can kind of get more footholds on the network. So if you lose your foothold on one box or one host, you have another host that's completely separate, and you won't get burnt out of an entire network if something goes awry. So for whatever reason, we're missing 6. I think it got moved. This kind of goes into why you're doing this in the first place and some of the things you can do after you've kind of gotten more footholds on the network. You've kind of gained control. I think that the next slide is supposed to be exfiltration. Yeah, exfiltration. So, you might block services for particular hosts. You might crash systems, set off alarms. You can do all kinds of crazy stuff. Typically in updating firewalls would be a cool one to block legitimate traffic. And there's an interesting case with I think it was SolarWinds where they actually modified the firewall to decrease the amount of traffic so it didn't look as suspicious. So very sophisticated stuff. But typically with what's up, Ethan?
6 was obfuscation / anti-forensics.
Oh, okay. So
I deleted that last week when I was writing slides. I hit delete instead of hide.
Oh,
Is that
okay.
an obfuscation technique?
Yeah, it was an obfuscation technique to remove it.
Oh, okay. I'll briefly cover that. So within an average assessment, I don't think denial of service is probably going to be too applicable because you're supposed to be serving the client, and by denying the service of the client, you're going directly against them. So I don't know how relevant this is. Obfuscation, you might cover your tracks. So you might go back and delete persistence mechanisms or you might delete processes if something went wrong. So it's a cleaner operation, and so so that a blue team coming in behind you doesn't necessarily or is not able to recognize that you're actually there. So that's one way you might obfuscate yourself. You might delete logs or something along those lines. Exfiltration. This is a big one within most attacks because I think the incentive of a lot of hackers is to pull data. So another recent thing was a T-Mobile attack. I think that was maybe 2 weeks ago, where someone was able to get into the T-Mobile network and pull this massive database of social security numbers and phone numbers and last names and really bad stuff. So exfiltration that's an example of exfiltration. So you're pulling data off the system or off of the network, and you might wonder, what are you pulling? How are you going to move it? Are you going to encrypt it beforehand? Are you going to zip it so it's smaller and less likely to get caught by firewalls or by a defender? Things to consider. But I think, that is it. So are there any questions before we move on to cryptography at all? I will take that silence as a no. Well, all right. So we're going to move on to cryptography. I think Tripp's got
setting up a document camera to do some pen and paper stuff. Because some of this is kind of visual, and it might help to sort of create things as we go. So how's the volume on? I need a way to Or can someone let me know if someone says anything in the Discord?
Yeah, we'll let you know.
Okay, cool. Awesome. All right, so yeah, this is going to be a little weird, a little different than the standard format. So I wanted to kind of change things up and not look at like an overview of cryptography as a whole or something like that and hit the bullet points and stuff. Hey, I wanted to sort of like start at the basics, cover some building blocks, and then kind of see what we could come up with, either as like a full collaborative exercise, or if we want to turn it into like a group-based thing, as far as like building our own sort of reasonably secure block ciphers. I say reasonably secure because that is a generally difficult task requiring much more knowledge than I have. Block ciphers are the product of, or well, ciphers these days are the product of many people and whole communities worth of research and stuff. But we're going to do it pretty easily, I think, by ignoring one very particular goal of modern day ciphers, and that is that they have to be performant. So if we disregard any sort of desire for efficiency and go for infinite computational resources, we don't care how long it takes, it's actually not too difficult to see how things like AES work in modern day block ciphers. So yeah, with that said, I think I'm going to try and sort of go over some of the basics, sort of the building block stuff. So some of this is going to be either old stuff to you or just seem very fundamental, but it's sort of, it still helps to sort of go through things from first principles sometimes. So yeah, let's see. How does, that is a very high resolution picture of my hand.
So you
You
can
can
zoom out more.
Okay. No, I mean that's fine. That's cool. A modern day document camera. You can see how like gnarly my nails are, but all right, so Cryptography 101. So we're going to start with substitution ciphers, because those are sort of a class of ciphers, or a class of encryption, decryption operations that are found, or that are found in as they're sort of parts of complicated crypto systems like AES. So a substitution cipher involves an alphabet, sort of where you're taking characters from one alphabet and mapping them to characters in another alphabet. So an alphabet is just a set of, like in our case, we could use the English alphabet of capital letters. It's just a set of characters of whatever you want to call them. It's a collection, and so forth. So a key in a substitution cipher is kind of just a mapping from that alphabet to a permutation of that. So let's see, if we want to come up with a simple English substitution cipher, we could swap A with, actually, there's computers for randomness, so let me shuffle things around and see what comes out. By the way, if I want to like hot swap things from the document camera to like Python or something, would that be just changing the HDMI cord, or?
There's like 2 you have to change.
Oh no.
You need
This.
It's not trivial.
Oh my god. So there's the one from.
So we'll have to close the.
Oh no.
Make sure to change.
All right, we have visuals of a terminal
Well, they decided to disappear.
that just. Okay, I just.
Okay. Wait.
Why would it have disappeared? So is the general solution just like toggle stuff back and plug it out and let the magic work?
We go back to this. And then
That's
back
what
here.
I just said. Okay.
That's his
Yeah,
laptop.
this is
Oh, okay. Don't
cool.
Don't touch it. Yeah.
All right. So yeah. Dot. Is it uppercase? String dot ASCII uppercase or something. What was the thing from? All right, back to DocCam.
Oh yeah, we can actually do this. Just leave it on laptop. That might be easier. Cool.
Okay. All right. So say we want to shuffle this to D, G, A, C, B. I've got A. I can take G and back to H. So let's restrict our thing here and F. And does that cover everything?
G's in there twice.
I have
is that
G's.
right?
All right, let me change that to an E. All right. So now we're restricting our alphabet to the first 8 letters and just mapping them according to this shuffled permutation here. Yeah.
What rule are you following?
That was just random, like whatever I could come up with. I was looking through here, picking that. All right, find this one, pick that, and that sort of thing. Not a good way to go about randomly doing things, because people are bad at randomness. If you want to go through with like, or if you want modern day randomness, you use a computer basically, which is paradoxical, but they have they have good systems in place to generate random bytes. But yeah, so if we want to encrypt which I now have to like figure out a word that's only out of this restricted. So if we want to encrypt dead beef, because that's the common sort of word that people make out of hex digits, we just look at each letter in the sort of original alphabet, map them according to this key here. So D gets replaced with C, E gets replaced with B, A gets replaced with D, and so forth. What? Wait, I've messed that up. E goes to B, and G. Okay. So now we have sort of from plain text we get ciphertext, and to go back, it's the sort of inverse operation. So rather than mapping from this ordering to this ordering, we go backwards to the same way we came from. And that's sort of a key feature of just the encryption-decryption operations is they need to be invertible, or they need to be, you need to be able to recover the plain text from the ciphertext using, with knowledge of the key, because otherwise it'd be very easy to make things unreadable to anybody just by mangling things up. So yeah, and that's the basic principle of a substitution cipher. Or in this case, well, this is a monoalphabetic substitution cipher because we go from each letter maps to one letter in the ciphertext alphabet. There's no so there's things called polyalphabetic ciphers that involve, say, like A could map to a choice between D or some other letter that, whatever letter we want, Z, and that's sort of can make things a little bit more complicated, but not really. The zodiac ciphers, if you remember the sort of substitution cipher puzzle that we looked at last, what was it, 2 or 3 meetings ago when we were doing the mock CTF stuff. The zodiac ciphers are polyalphabetic substitution ciphers. Their strength, or why it was just a couple of years ago that, or was it maybe like last year that the latest zodiac cipher was cracked with like modern day computers and everything. The strength of that is not because of the inherently strong cipher, it's just because of a lack of actual ciphertext. December, okay, yeah. Yeah, so that's pretty long time for just handwritten symbol cipher. But yeah, that's just due to like, it can actually become very difficult to decrypt or to do, like say you were just given this string here, or just given this string here with no this is all the ciphertext you have to go off of. That could be, well, we're also in a restricted 8-letter alphabet, but you don't have, other than knowing that this letter was repeated, there's not too much about the like structure of the plain text word that you can go off of, just because of having 4 characters just isn't much. Yeah, and as you sort of noticed, the things like repeated letters, commonly used phrases, like if we were back to the original full English alphabet, commonly used words like the, is, a, etc., especially if you're not, if you're maintaining spaces so that you know the word links, it becomes very easy to sort of figure out which mapping, to figure out those mappings just by knowing, sort of taking a guess at what the plain text might be. So yeah, let's see. The chief issue with this is that, well, it doesn't do anything with the structure of the underlying plain text, like without getting too like detailed or anything, because I want this to be very like self-contained talk, but it doesn't mess with the probability distribution of the plain text, because the E is the most common letter in the English alphabet, and it will always map to the same letter under a monoalphabetic substitution cipher, and so we can look at like frequency distributions and stuff of the resulting ciphertext and sort of match those to the original characters that they should be. And that's one way to sort of figure out the actual substitution being used and so forth. So now I wanted to sort of look at a sort of subset of, or well, first, I guess, back in our original example, we had eight letters in our alphabet, the 6 hex digits plus A, B, C, D, E, F, G, and H. So plus G and H. Yeah, there are 6 hex digits. Okay. And we mapped them to D, E, A, C, B, G, H, F. So I noticed, or when I mentioned that like the key is just sort of a permutation of the original alphabet here, we can sort of figure out how many substitution ciphers are possible. Like if we wanted to, if we're just taking the original alphabet, mapping it back into itself, so another 8-letter alphabet, we can choose, like, for the first letter, we could choose to map it however we wanted to, or we could choose whatever character we wanted to. So we could choose D, we could choose B, C, so forth, for like what we map A to. We could also map A back to itself, be a sort of fixed point. Now, after we've chosen that, so there's 8 choices for that, and after we choose that, then there's now 7 remaining symbols to go off of, and so 7 choices there, and then the next letter there's 6 choices, and so on and so forth. You get the sort of permutation counting problem for how many ways can you permute 8 symbols. It's just 8 factorial or whatever. 8 times 7 times 6 times 5 after, yeah. Now, that would be pretty difficult to brute force if we, say, increased the alphabet size from just 8 characters to like 256 bytes. If we were looking at like substituting each byte in a sort of binary blob of plain text, switching that with some other, one of the other 256 bytes, then you're looking at brute forcing 256 factorial possible ways of permuting that, and that's pretty infeasible. So I mean, it is a weak cipher in the sense that you can use this sort of known structure of the plaintext, or if you had any sort of known plaintext ciphertext pairs, you would be able to figure out the permutation very easily just by, or you would be able to figure out the key very easily just by looking at the known, I mean, in this case, if we knew what was our, yeah, if we knew this pair already, we would know that like D maps to C wherever and so forth. In the E maps to B, A maps to D, and so on. We would be able to use that to like anytime we ever saw a C in the ciphertext, we would know what it is. So yeah, it doesn't hold up to what's called known plain text attacks, and doesn't really hold up to guessed plain text attacks because you can sort of figure out what the plain text is by known frequencies of the English alphabet or something like that. So now, let's see. Can we go into, yeah, let's look at Zor ciphers, because those are another common sort of building block. So Zor is a logical operation between with the truth table. Wait, did I? Yeah, 1 where they're different, 0 where they're the same. So if you have two sort of binary variables or Boolean values that can take 0 or 1, Zor is just the operation of if they're both 0, they're 0. If they're both 1, they're 0. Or returns false if both of them are the same, returns true if they're different. Now, how does that scale for, say, strings of bits? So we have 1, 0, 1, 0, just a couple of what might be somewhere in the range of ASCII. Possibly. Nah, well, yeah. These are 8 bit strings or octets or bytes or whatever you want to call them that could represent some of those ASCII characters that we were looking at for our sort of original substitution cipher alphabet. And they just happen to line up very close to each other. So if we Zor these two, we sort of look at it like bitwise. So looking at the bits as they line up, Zor or run this Zor operation on each individual bit, and we get 0 where they're all the same and 1 where they're different. This is also sort of modular 2 addition, where you're adding each of the elements, or you're adding each of the bits mod 2, so you never go up to, like, you never, instead of counting up to 2, you just wrap back down to 0. So yeah, 1 plus 1 is 2, and then wraps back down to 0, and so forth. The importance of being modular addition, or sort of like modular addition, comes into play when it comes to figuring out, or when it comes to like a concept of linearity in cryptography, where if something can be written as like a sum of without going into like the definition of it, because it's hard to, really describe linearity when you're talking about like bit strings and everything. Zor is sort of a classic linear operation, and is used in cryptography pretty often because of because of its ability to, like, if this were some random string of bits, you could apply that to some structured string of bits, and you get a random string of bits out, or what looks like random string of bits out. You can sort of take the randomness of some bit and mask it into the non-random or randomness of some byte here and mask it into the non-randomness of another, and well, we'll see that in a second. But yeah. Now for, anyways, I don't know where I was going with the modular addition stuff, linearity just yet. But yeah. So a Zor cipher is done essentially like that. It's taking a string of unknown bits, Zoring it over a string of like what could be plain text, and you get garbled output on the you get output that's masked by that string of plain text. So the chief thing with encryption is that we want it to be safe against an attacker that knows the plain text, an attacker that knows or an adversary that knows the plain text, and the obviously the ciphertext, because the ciphertext is sort of thrown out into the public. But we don't want it to be, or we want all of the sort of unknownness, all of the inability to take the ciphertext and turn it back into the plain text. We want all of that to come from the unknown value that is the key, whatever that is. So if we were to say our key is some random string of binary digits, like literally a random string. So like, say we choose 32 bits of randomness. And I'm not going to draw out 32 bits. So let's say we choose 8 bits of randomness and actually do it random so that I can let's see. And I would show what I was doing, but kind of projector issues. So grabbing just a random byte from the Linux RNG, which is dev random. It's sort of a system built inside the Linux operating system that grabs or maintains a pool of randomness for uses like generating cryptographic keys and stuff, which I would also have up on the board if I to be pointing to, but yeah. All right, so we got the byte 23. So that 0010 0013. So hex 23 was our random key, which is almost strikingly similar to one of these keys in reverse, but yeah. Anyways, there's only, 256 possible bytes to choose from, and we chose that. Main thing being we chose it uniformly random, so that if someone were to not know that value, the best way they would have to guess that value is to just brute force it, to go, when they have a plain text and ciphertext pair, brute force that value and figure out what it actually was. Actually, plain text and ciphertext pair and a Zor cipher is a dead giveaway because you can just Zor the two together and recover the key. But if they had that's another thing. The Zor cipher doesn't actually As I said, it's a sort of particular instance of a substitution cipher anyway, so it doesn't mask the plain, or it doesn't mask the distribution of the plaintext or the letter frequencies or any of that stuff. This kind of structure of it. That comes up with another operation later. So yeah, we have this key and we have a message like the ASCII byte A 00001. So we XOR them together, XOR them together, 0001110. We get our key shifted left by 1. Oh no, actually, yeah. Anyways, the actual bits here don't matter, but the main thing is that if this key here were to be, if I should indicate that's our key. Plain text. So if the key were truly just unknown, like pulled from random, we only used it here, and we encrypt the plain text with that, we send that over the wire, we're solid, because an attacker or an adversary, someone who catches that message just sees the ciphertext. Not knowing anything about the underlying plaintext or anything like that, that could decrypt to anything because of, if we choose any sort of guess at a XOR key, we don't really have anything to go off of when it decrypts. But the main limitation of that is that we chose our key to be the length of the plaintext itself, which is kind of a limitation if you wanted to just send arbitrarily long plaintext. If you need an equal amount of bits of random key to go with it, that's pretty expensive because there's the challenge of sort of creating this key, drawing it uniformly from random is one thing, getting it to whoever you're talking with is another thing entirely. What we really want is to be able to establish a key early on and then use it over and over and over again. So if we were to like reuse that, so say we had already shared this key with someone else and we wanted to reuse it to encrypt a longer message that's 2 bytes, like AT or whatever. 011. So we want to encrypt a 2-byte message with this key. And let's say the message is just AA, because that could be a message. 0110 0010 0110 0010. So we might think to just sort of extend the original single byte key, use it again on the next byte, and then if this message were like just an arbitrary length, we could keep that going, keep XORing it with whatever that original byte is, and so on and so forth. Does anyone see the sort of problem with doing something like that, with what the output, or thinking back to, yeah.
It's essentially the same as the substitution, where you can analyze the frequencies of light.
Yeah. Yeah, it's essentially it's a very particular substitution cipher, depending on whatever byte we have of plain, or whatever byte we have of the key, how that's going to XOR with any sort of or with any ASCII byte or anything like that. But it's a fixed substitution for any individual byte. So you have the same problems. You have the fact that you can recover, or that it doesn't do anything to mask the actual distribution of the plain text, and so on and so forth. It's just a useful building block to be used. It's not a secure in and of itself. And yeah, that's as we'll get to it later, we sort of need to add some non-linearities to it to the whole process in order to really carry this out. So since we're on the topic of looking at 8-byte substitutions and stuff, so substitutions on just any arbitrary 8 bytes, we can think about it, or we can look at these things called S boxes, which are a huge leap ahead of XOR ciphers and classical cryptography stuff. But they're essentially just substitutions. They're used to build substitution ciphers on 256, on some number of binary block, bytes, nibbles, every 6 bits. The actual sizes can vary, but yeah. So an S box is essentially a substitution on 8 bits. Or, well, an 8-bit input S box and an 8-bit output S box are just a substitution operation. So we take in, this could be any possible 8, or so this could be fed any sort of 8-bit input, and for each specific 8-bit, right, I'm going to start calling them like octets or something, because I feel like that's more, or less, and more phonetically distinct, I guess. So for any octet we feed in, we get a very specific octet out, and that's an S box. It's just a mapping from the alphabet of 0x0, 0x0, 0x01, and so forth, all the way up to 0xFF, all possible 8-bit bytes represented in hex, to that same alphabet, just in a substitution output, or on the output. Now, how is that achieved? So, well, for one, it's very important that these are one-to-one substitutions. So if we feed in like the byte hex FF, we get only one output, or well, sorry, for an output byte here, let's say it outputs the byte hex FF. There's only one possible input byte that goes to that, because otherwise we lose the ability to invert that. If we ever see this byte, because this can be inverted backwards if there's only one, let me think of a good, say the bit 110011, 1 0. So the byte hex 66 maps to the byte 1 1 1 1 1 1 1 1 because we already have FF over here. Yeah, the main. So when you're looking at things like substitutions, you just have to be able to go backwards as well because of encryption and decryption, that stuff. So each of these output bits is technically a Boolean function of all 8 input bits. By Boolean function, I just mean it takes Boolean variables, so whatever you want to call it, an octet, a byte, a vector of Boolean variables. It takes that, and depending on those values, it outputs 0 or 1. And that function can be arbitrary. It can be completely like, if these bytes are exactly 0, 1, 1, 0, 0, 0, or 1, 1, 0, then output 1. If they're something else, then output 0. That's the kind of design that this is going for. Now, looking at each individual bit is an important thing because of, or looking at it like that helps because as these are sort of applied in sort of a combination of operations, you want what's called this sort of avalanche effect. So like, if this bit were flipped to 1, you want that to kind of mangle this output in some weird, like, you want the difference between the output here to be as uncorrelatable as possible, as the uncorrelatable is basically, you flip one bit here, it has, each of these bits has a 50% probability of flipping is the goal. Because if they didn't, if you had some sort of issue with flipping one bit here, and that only caused like one bit to flip here, then you can sort of piece down the problem into like, you're not trying to figure out the substitution, but maybe if we just guess that this bit is 1, then we have some sort of knowledge about the then if we guess that this bit is set, and that bit being set only affects this bit here, then that gives us a kind of indication of, if we had knowledge of this bit, we would also have knowledge of this bit, really. Versus if this bit changes and flips everything, then we can't really go by the how this changes to really determine what that bit was to begin with. So the scope of it's very similar to making all of these input bits as interdependent with each other as possible. As far as this output bit here is going to be some extremely nonlinear function of all of these input bits because of, and by nonlinear in this case, you can think of it as just, you want these input bits to be as dependent on whatever the values are to start with, or to dependent on whatever the values of each other are is the key sort of term there, because that's how things can sort of be I want to say like changes can be sort of commingled together so that the output is unpredictable. Because once these are plugged into like a big composition of operations, if there's if like all of these are unknown, or well, you really get the sort of if they were unknown but known out here, then I won't go into that. But yeah, the basic idea behind these, or well, the idea behind these is that they're not that basic. There's a lot of work has been into sort of figuring out the maximally nonlinear functions to choose that still, because remember these have to like come out as, these have to maintain that sort of one-to-one function between the input bytes and the output bytes, because they have to be plugged into it, or they have to work both directions. And that solving that challenge is pretty extensive and beyond the scope of my knowledge by far, beyond the scope of anything we could tackle in here. That was a lot of work in like the 80s, 70s, 90s really in designing these. And so for our purposes, we're not gonna like try and figure out, you know, do we AND these two bits together? Do we then XOR them to this? And then AND these together to output this bit here, and that sort of thing, because that's complicated. We're just going to sort of say that people have figured this problem out and figured out if they can be trusted, we'll assume that their S boxes are solid, that they achieve the properties that we want. Those people being the people that designed AES. So there's, if you look up the there's a J in here somewhere. The Rindale S boxes, you can find like basically a lookup table for, since this is just a substitution cipher between bytes, you can find just a lookup table for what to use as your S boxes. And that's kind of a good go-to in like sort of cryptography stuff. You know, use the known solutions rather than try and build something yourself, even though we're, you know, eventually going to try and build up a cipher ourselves. We're not entirely building it ourselves because there's just a lot of research that goes into these, and we're just going to like pick the S boxes that they came up with. And also within that, we're also trusting that these, what are now constants in the encryption algorithm that we're using, because these are just lookup tables. Anytime you see this particular configuration of bytes, you swap it with these bytes. Those are just constants that can be hard-coded into a program. Because of that, there's a good bit of they look a little sketchy if you're just sort of using them and trusting them to have the properties that you want, because it's really hard to achieve those properties. And yeah, we're just sort of going on trust, and people will not use AES because it is an American cipher. That's a valid, like, if you knew of shenanigans that went on with let's see, what is it, Dual EC, the and other potentially backdoored stuff. There's a lot of paranoia about that, and it's not, you know, entirely unjustified. So if you don't use AES these days, the sort of Cha-Cha 20 is sort of the standard alternate stream cipher to it. It's That's a Daniel J. Bernstein cipher. Not made by the American government, made by a person that sued the American government or that fought the American government in court to get their Salsa 20 out, or stream cipher exported, or make it exportable. Yeah, anyways, interesting history around the 80s or 90s and 2000s, turn of the century type cryptography stuff. But yeah, that's an S-box. And if you realize, if we just sort of use, I mean, that is still just a substitution cipher. It's better than a XOR because of how XOR is very linear with the input bits going into the being XORed with some key and coming out. And I really need to like look at the paper when I'm writing, because trying to like look left and observe it on the thing is weird. So yeah, the XOR being a more linear operation, it doesn't really do much to like scramble these bits against more stronger cryptanalysis stuff. But if we swap it into, and if you knew all of the bits going into either the input or the output of an S-box, you would know what all of the bits on the other side were, because of it's a fixed transformation. But the key is, once that's packaged inside of this whole tornado of bit operations and stuff, it becomes very difficult to know what the bits on one side or the other is, and that's the difficulty that we want to achieve, basically. So yeah, and I have like a sort of substitution cipher example, or was it an example? A puzzle, I guess, that we can do that kind of goes into some, some of the problems of what happens if you have structured input, or if you're, dealing with sorry, not structured input. If you're using like a, well, I don't want to give too much of it away, but as we've mentioned, substitution ciphers are very, well, they don't hide frequencies of the internal or of the underlying plaintext. So now back to figuring out how to get this. So it's on the mock CTF server.
You gonna swap to your computer, or are you just gonna?
I think I'll just swap to the computer for.
Yeah. We can.
Yes,
Oh yes.
it works. So.
Well, it did. Oh gosh. Well.
I'll be logging in and typing in my ultra secret mock CTF password while the screen is down and it's being broadcast to the internet. Bet you can't guess that password.
I don't know why this is broken.
That is. So where does the video feed actually like plug into this monitor or the screen?
Right. I mean, this is going to the screen.
Okay.
This cable somewhere. Everything.
Yeah, I think that's how we solved it one time. Laptop, plug it back in. Take it out. All right, so if you go to the mock CTF website, there's a cryptography 1001 challenge that I'll hopefully pull up in a second.
Oh,
Yeah, on AUEHC or
So if they're virtual, they need to be on.
right. Yes, that's a
We explain how to do that in the first week.
yeah. And if you don't want to pull it up, that's also fine. I can yeah.
Wait, how much is this worth? Is this worth 1,001?
yeah, that just should be easy to find. So
Yeah.
It's like on the end.
It's very similar to